take this guy for testing the error. I mean, you can switch with these chunks, that becomes a 5-fold CV thing for your entire model. So again, so here to start with, I'm setting this as null, which we created earlier. The first, and I'm not doing the 5-fold thing here, again, too complex to implement. Although, if you want to take note, there are in package caret ensemble and caret stack function which you can make use of. I'm not making use of them so that the idea which we are trying to implement should be clear to you. Instead of using that 5 or 4-fold thing, I'm just breaking my data into 2 parts. I'm building this on train A. I'm again building the first layer of model on train B. Right? So I'm leaving one chunk out. And then, so let me show you this here as well. So these are two, and test data is separate that I've put aside for checking the errors. I'm building my first layer of models on this A guy, train A. Then I'm building first layer of model on B. That is what I'm doing here. And next, what we will do, make use of build model which we built here, make predictions here. The model which we built using this data, we will use that to make predictions here. Yeah? Okay. Can I move on? Yeah. So here on train A data, I am making predictions using GBM-B, the model which I built on train B using GBM. And similarly on train B, I am making predictions using GBM-A. Okay. Now when we again, I'm using probabilities. We discussed why. Because I don't want to unnecessarily smooth out the information that I've extracted anyway. And then I am combining the entire data back. The train is basically, or I could have used the original one, but anyway, I have the data back here. And then the layer 2 is built on the entire train data and utilizing the out of sample predictions or feature coming out from GBM. Okay. Now I make the full model, GBM full, on both the data taken together, that first layer of model again, and use that to make the GBM feature on the test data. And then the second layer of model that I have built, I'm making use of that as prediction on the test data. Let me repeat the process again. I know it kind of gets confusing. Till this point, everything is clear, right? Yeah? Okay. Then I am combining both of these guys. And I am building my second layer of model, or rather I'm going to build my second layer of model. The sequence is, I guess, might be good. So I'm building my second layer of model here. Okay. Now, because I want to get the value of this GBM variable on my test data, I am again building this GBM model on the entire full data, and then I'm making prediction on the test data so that I can use that variable when I'm making prediction using second layer model. Okay. Here again, I have used some threshold which I knew because I worked with this data before that it might work. Okay, that doesn't mean this is the most best threshold out there. You might want to get it using either your custom matrix or KS or whatever. We again get slightly different results. There is an improvement in accuracy. There is no, I mean, there might be some decimal difference later on, but as such, there is no difference in F1 score. you actually end up losing on recall. It turns bad, and you make the trade-off in terms of precision. Okay. The idea here is that you should be see, at the end of the day, you are solving a business problem using the data that you have. Never get lost in algorithms because you're using something exotic, you're using something complex. Because I used a complex algorithm, I made a better model. No. Eventually, you should be very, very clear about what your business goal is. Is it improving precision? Is it improving recall? Is it important to consider both at once? Or you are okay with as long as the accuracy is higher, you don't care about the sensitivity or in terms of precision and recall. So that will basically decide your choice of model. Do I really want to do that? Or how do I want to tune my parameters? Okay. Yeah. Yeah. Okay, you're talking about parameters. Yeah, I have not. I just wanted to keep things simple so that the focus remains on ensembling and we do not get lost into parameter tuning as such. Okay, I guess that is something you can explore on your own. In fact, if you have mentioned here, I don't really like R on that when it comes to tune a lot of parameters, especially in case of GBM or take XGBoost as such. I randomized grid search. Although normal grid search does come with package, I think if I recall correctly, CV tools. Has anyone used that? I think it does come with normal grid search, but randomized grid search is not there, which lets you reduce the time which goes into parameter tuning. So yeah, if you want to use that, do utilize randomized grid search in Python. Coming back to okay, it seems we lost the presentation. Oh. Well, it's like if it's available, why not? If it ends up improving performance, then why not? Yeah, it's a technique which is available, and if you looked at the code, it doesn't look like not accessible. Syntax might look very arcane if you haven't used R before as such. Yeah.
My goal was to increase the recall so that I have very few false negatives, but I don't care much about your false positives.
Right.
In that case, would this ensemble strategy change? If I wanted to, checking on disease or heart attack or cancer, I want to make sure I don't have very many false negatives at all. But I don't mind false positives because I can put the patient through.
I think the meta classifier that you're building, you can tweak the loss function which is being optimized there in order to give more weightage to misclassifications of negative or positive as what you want. Yeah. I guess when you tweak the loss function for meta classifier, the variable will contribute differently in a sense. The strategy as such might not change. Okay, so it doesn't stop here. There are a few ideas which I haven't discussed. Yeah. Yes. No. I'm not. So the full model, if you see here, the full model that I've built, I'm not. This prediction of full models are going to test. I am not using prediction of the full model back to the data which was used to build it. Okay, that clarity is there. Yeah. Okay. More ideas which you can explore is about how you can use features. If you are working with a classification model, you might build a regression model anyway, and use that as a feature. If you are working with a regression model, you might build a classification model anyway in order to extract that feature. So what is the point of doing that? The point of doing that is, in a way, when you're using ensembles, when you're using GBM, think about it this way: all these models I'm not using for making predictions. I'm using them to extract some variable transformation which doesn't have an explicit function. Okay, so that it can extract patterns which we try to emulate by variable transformations in a very generic way. Okay. Another idea is, and then which is not something which people have not explored. I think that is instead of, so for example, you group your data and you might decide to build different models for each group. Instead of doing that, use that grouping as a variable itself, so that you for the rest of the, you end up making the complete pattern which is present in the all data, instead of using different models for small chunks of the data. And these can be from PCA, from k-means. TSNE is something which you cannot use because I think, how many of you were attending Nishant Chandra's talk? Yeah, so TSNE does grouping very well, and in many cases much better than other grouping or segmentation algorithms, but you cannot use that as a feature because you cannot make predictions with TSNE. Why do I mention that? Because it might become possible in very near future. The functionality for prediction was there for a while in one of the Python packages. I'm forgetting the name, but they later found out that there was some error and that functionality has since been taken out, but it might come back. And then instead of k-means grouping, you might want to use TSNE because, you know, in many cases it works much better. Okay. To summarize this, it's not a typical revision or rather repetition of everything that we have covered. We discussed that when you are combining models, it is better to combine models which are inherently capturing different patterns in your data, or they are designed in a manner that they extract patterns in different ways and end up capturing different kind of patterns from your data. So you can try SVM, decision trees, KNN, GBM, RF, neural nets, ED. Although you might want to keep your neural nets shallow, because if you're using very large neural nets, you know, it doesn't remain fair for all other models. They end up capturing whatever niche pattern there are in the data. And the ensembling is something which might not be very useful in that scenario. Also, yeah, I mean, RF, ET, and D trees are going to be fairly correlated because they are mostly work on similar algorithms. This part is something just to keep things simple I have not covered, but so the last part where I said that you can use this chunk which you're keeping for test, you can you know, use this for test and calculate error here, and use this test and calculate error here, and so on, and the average of that or any median or however you want to calculate the cross validation error. Don't blindly take error or median or whatever as the indication of the error. Do look at the variation in different chunk errors also. Why am I asking you to do that? If you just look at the mean value of the CV error, you might end up assuming that, okay, this is the best indicator and this is the generalization of the error that I'm getting, and you will blindly make prediction on the test data. What might happen, that if the different chunk errors are very different from each other, which means your model is not generalizing very well, and it might not perform as well as you're expecting on the test data or on which you want to make predictions. So that is why when you're looking at CV, you should look at variations as well. Okay, that's gone again. It's all right. The third point that I wanted to clarify, and I have I think by now I've mentioned that many times, we are at times are not very comfortable with using complex algorithm because somehow there is this factor that it should be intuitive. I'm not able to find out how one variable is contributing to this model. To make peace with that thought, you can consider these algorithms as exotic variable transformation. For example, we very comfortably use credit score, right? And it doesn't really bother us, but have you ever thought about how this credit score is being built? What all modeling processes are going behind that? It is one example of some kind of ensemble methods that you have been using all along without really realizing about it. Yeah? Okay. And this, although with all those packages coming up which support stacking and ensembling in general, the leakage of information is becoming less and less dangerous. But yeah, I mean, be always careful about this. Whereas you don't end up using the information from the same data again to build your model. Okay? Yeah, that's about it. Thank you so much. Thank you for your patience. Yeah. And if things haven't made sense, don't worry about it. If you come back to what happens is if you come back to it again, it probably start to click. Yeah.
Yeah. Thanks for this session. Now I think it's more or less mainstream. The people are, especially because of Kaggle, people have started using it. But in your experience, it's a slightly different question. It's not technical. When you present ensemble models, right, you pretty much always met with some sort of resistance by the keep it simple kind of
right.
How do you, in your experience, what's the best way to handle such people?
Well, don't tell them what method you're using. And I'm not joking. Let me complete that thought. Start with the discussion on performance rather than the method that you have used. Okay. If they're so much opposed to the idea, or rather they want to keep things simple, tell them that you are. I shouldn't say that. You can, instead of saying that you are using ensemble methods, first layer, second layer to make it complex, you can pose it like these are the scores that you have developed. So call GBM model as a score that you have developed, a variable or a data product that you have come up with, which helps doing prediction better. I mean, that is one idea you can say. Also, I think 5 years back, using random forest was a big deal. It's not anymore. More and more across organization, people are using random forest. They have kind of become comfortable with the idea. So I guess you can wait for people to become comfortable about it. That is one thing. Yeah.
When we do ensembling, we are talking about at least processing time increasing by 5 times or more, depending on how many data chunks you break into, right? You will have to learn many times, you have to layer. And if the increment in performance is only like 78 to 79 or 78 to 80, then does it even make sense? So, in your experience, have you seen like performance jumping significantly that we can ignore the processing time which increases?
I think practically that is not a big concern, in the sense that I have seen when you are working on business problem solutions, not talking about Kaggle as such. Business problem solutions, you try tons of ideas, you try tons of algorithms, and you end up choosing one which is performing better, right? So I don't think you really care about the modeling time as such anyway, because you want to try as many algorithms as you want, and this is one of them. So what the processing time increases.
But then you have to always run it on your data, right? It's not only modeling.
Right, and sometimes it might not result into a better performance, right? But generally it might. So, yeah.
So I have a very open and real case where I built an ensemble of two models.
one was from a bigger data and other one was from a smaller data nested in the bigger data. And the reason was a class of factors had high missing value percentage on a particular subset of data. So, like factors which had better fill rates were used in the bigger model, and factors which had high missing rates were used in the smaller model, and I was trying to ensemble them. So my question is like, when we tried ensembling them, like the model built on a bigger data became the dominant.